Mount St. Helens in Washington state is one of the most well-monitored volcanoes on the planet, and with good reason. It is still active.
Well, Mount St. Helens has been a little more active than you may expect this year. Since February 1st, there have been 350 earthquakes taking place on the mountain.
Picture standing at the edge of a vast crater where the earth once tore itself open with unimaginable force. Beneath your feet lies a slumbering titan, Mount St. Helens. It's been decades since its last major eruption, but the signs are returning. Deep rumbles, rising gases, subtle tremors. This volcano once changed the course of geological science forever, and now it may be preparing to do so again. Could the Pacific Northwest be on the verge of another earth-shaking event? Whispers beneath the earth. In early 1980, subtle hints of turmoil began. Earthquakes tickled the mountain's core, each one stronger than the last. Within weeks, geologists documented massive bulges swelling the northern slope, a clear sign that magma was gathering below. Then came May 18th. At 8:32 a.m., a magnitude 5.1 earthquake hit, and in seconds, the entire north face of the volcano collapsed. It was the largest landslide in recorded history. What followed was a violent lateral blast, an explosion so intense it leveled forests for miles, scorched wildlife, and filled the sky with ash that drifted as far as the central U.S. The ash column shot 15 miles into the atmosphere, grounding flights and painting skies an eerie gray. Mount St. Helens had awakened, and nothing would be the same. The aftermath of ruin. For miles around, silence settled over a dead landscape. Rivers were clogged with debris, once green hills became gray dunes, and the ecosystem teetered on the edge of collapse. Life had been scraped from the mountain like chalk from a blackboard. Yet amid the devastation, geologists saw something else: opportunity. The eruption offered an unprecedented chance to observe, in real time, how life begins again from nothing. Even as ash cooled, the land was already transforming. Steam vents hissed from within the crater, indicating that magma hadn't retreated. It had merely paused. The mountain still breathed. A new era of observation. In the years since that catastrophic eruption, Mount St. Helens has been under constant watch. GPS instruments, satellite imagery, gas sensors, and seismic arrays, scientists have built one of the most advanced volcano monitoring systems in the world. The data they gather is not only continuous, but increasingly granular, able to detect minute shifts in pressure, temperature, and elevation that would have gone unnoticed just a decade ago. And lately, those instruments have started to whisper familiar warnings, triggering a wave of renewed analysis and vigilance. Clusters of small earthquakes, deep but persistent, are now appearing once again beneath the volcano. These tremors are not random. They trace the rise of magma through fractures in the crust, pressure mounting like steam inside a sealed chamber. Many of these quakes occur in patterns known as seismic swarms, dozens of quakes in rapid succession, typically associated with the movement of magma or volcanic fluids. Scientists have noted that the locations of these swarms are not limited to the areas affected during the 1980 eruption, raising new questions about changes in the volcano's internal architecture. At the same time, surface measurements reveal subtle uplift, indicating something below is pushing the Earth upward. These deformations, though often less than a centimeter in magnitude, are vital clues in the broader puzzle. When tracked over weeks and months using both satellite radar and stationary GPS stations, even small surface movements help create a three-dimensional picture of magma migration, pressure accumulation, and the structure of the volcanic plumbing system. Together, These seismic and surface changes are being interpreted not in isolation, but as pieces of a dynamic and increasingly detailed model of what might come next. The chemistry of a warning. Even more concerning are the gases. Sensors have detected elevated emissions of carbon dioxide and sulfur dioxide, both known byproducts of rising magma. The balance of gases has shifted, and researchers know this is often the prelude to volcanic unrest. While no single indicator guarantees an eruption, the combination of seismic swarms, ground deformation, and chemical changes is an unmistakable sign that Mount St. Helens is entering a new phase. Is it a years-long recharge? Or is this the beginning of something far more immediate? In 2025, a series of groundbreaking discoveries and technological advancements have given scientists fresh perspectives on its current behavior and future risks. These latest findings not only deepen our understanding of the volcano's recharging processes, but also shed light on the long-term ecological transformation of its landscape. Here are the most compelling updates shaping the Mount St. Helens story today. Increased seismic activity suggests magma recharge. Since early 2024, Mount St. Helens has experienced a notable uptick in seismic activity, an observation that has drawn the focused attention of geologists across the globe. Over 350 earthquakes were recorded between February and June 2024, with a marked spike in activity during the first week of June. While the majority of these quakes were below magnitude 2.0 and imperceptible to humans, their clustered nature and shallow depths were striking. These patterns are consistent with the movement of magma pushing its way upward through fractures in the Earth's crust, a process that builds pressure within the volcano and signals reactivation. Using data from seismometers, scientists noticed that many of the quakes were forming in tight swarms, primarily beneath the south and southeast flanks of the mountain, an area not as closely associated with previous dome-building eruptions. This unexpected location of seismic activity has raised new questions about the current plumbing system beneath the volcano. Some researchers believe it may indicate the development of a new conduit for magma migration. What adds even more intrigue to the data is the evolving nature of the quakes themselves. Initially dominated by high-frequency, brittle failure events, which suggest rock cracking under stress, later swarms began to include more low-frequency, long-period quakes. These are generally interpreted as signals of fluid or gas movement and can be precursors to eruptive behavior. The transition hints at a shift from mechanical adjustments to magmatic intrusion. Further bolstering the case for magma recharge, GPS stations around the volcano recorded measurable inflation of the ground surface. Though the uplift was subtle, less than 2 centimeters over several months, it matched the timing and location of the earthquake swarms, strongly suggesting that magma was accumulating at shallow depths. Scientists are using this deformation data in tandem with earthquake mapping to refine their models of the subsurface magma chambers. Advanced analytical tools like machine learning have also been deployed to sift through the vast data sets gathered during this recent seismic uptick. By training algorithms on patterns from previous eruption cycles, researchers are able to predict with higher confidence whether current events match historical precursors or diverge in ways that might suggest a new type of eruption scenario. While this activity doesn't guarantee that an eruption is imminent, it undeniably points to significant changes within the volcano. Mount St. Helens appears to be entering a new phase in its life cycle, one that warrants close observation. The convergence of modern data analysis, field measurements, and real-time satellite monitoring provides scientists with a dynamic view of what's unfolding beneath the mountain, and that view is becoming increasingly active. Satellite imagery reveals landscape changes. In February 2025, satellite images from the European Space Agency's Sentinel-2 mission revealed striking changes in vegetation and subtle ground deformation on and around Mount St. Helens. The high-resolution imagery, captured over multiple passes, allowed scientists to compare current surface conditions with past data, highlighting how both geological and ecological processes are actively reshaping the mountain's landscape. The imagery revealed irregularities in vegetation density patterns, suggesting that some areas of regrowth are experiencing renewed stress. This could be the result of underground heat sources or shallow magma activity subtly altering soil composition and moisture retention. In some regions, plant dieback correlated with newly detected thermal anomalies, prompting researchers to investigate whether volcanic gases might be seeping through the ground. More notably, subtle but widespread ground deformation was captured via interferometric techniques using satellite radar data. These deformations, measured in centimeters, appeared along a broad swath of the volcano's western and southern flanks. While the changes were not dramatic enough to be visible on foot, they revealed a pattern of slow inflation, a telltale sign that pressure is building beneath the surface, likely from a replenishing magma chamber. The Sentinel-2 mission's multispectral sensors also provided new insights into vegetation health. Scientists analyzed infrared reflectance to determine plant vigor across the blast zone. Surprisingly, some zones closer to the crater, which had shown strong regrowth in previous years, exhibited signs of stress and reduced chlorophyll levels. This change may indicate early ecological responses to changes in gas emissions or microclimatic shifts triggered by subterranean activity. These satellite observations are being paired with drone-based aerial surveys and on-the-ground vegetation plots to verify and refine findings. The integration of remote sensing data with fieldwork is giving scientists an unprecedented, layered understanding of how ecological and volcanic dynamics are intertwined. Together, these developments underscore the dual role of satellite imagery, not just as a tool for tracking volcanic risk, but also as a lens into the evolving health of ecosystems recovering from catastrophic events. As Mount St. Helens continues to shift and adapt, technology like Sentinel-2 helps ensure no detail, no matter how small, is overlooked. Gophers' role in ecosystem recovery. A 2024 study highlighted the essential role of pocket gophers in the post-eruption recovery of Mount St. Helens, a discovery that continues to reshape how scientists understand ecological succession after catastrophic events. These unassuming rodents became unexpected heroes in one of the most studied landscapes in the world. Shortly after the 1980 eruption, the landscape surrounding the volcano was thought to be almost entirely sterile. However, researchers began noticing isolated patches of greenery that defied expectations. Upon closer inspection, they realized that these thriving zones were closely linked to gopher activity. The gophers, which had survived in underground burrows during the blast, had immediately resumed their natural digging behavior. By tunneling through dense layers of volcanic ash and pulverized rock, the gophers physically mixed the nutrient-poor surface material with deeper, richer soil layers. Their movement helped create air pockets and microhabitats, allowing oxygen and moisture to penetrate and support microbial activity. This, in turn, stimulated the growth of nitrogen-fixing bacteria and fungi. which formed symbiotic relationships with pioneering plant species such as lupines. Moreover, the gopher tunnels served as protected pathways for seeds, spores, and even small insects. In some cases, seeds that would have perished on the surface were deposited into the gopher-created chambers, where conditions were more favorable for germination. These rodent-constructed refuges essentially acted as incubators for early ecosystem development. New data collected in 2023 and 2024, using thermal imaging and ground-penetrating radar, revealed that gopher tunnels had not only persisted, but expanded across large sections of the blast zone. These networks correlated with areas of advanced vegetation recovery, suggesting that their long-term impact was even more profound than previously thought. Interestingly, scientists also found that gopher activity promoted biodiversity in other ways. Their constant soil disturbance created a mosaic of microenvironments, encouraging different species of plants to establish themselves at various intervals. This patchy landscape turned out to be more resilient to environmental stressors like drought, heat waves, and soil erosion. This revelation has prompted ecologists to rethink the role of keystone species in disturbed environments. What was once considered a minor player in post-eruption recovery is now seen as a foundational agent of ecological resilience. The pocket gophers of Mount St. Helens have become a case study in how small organisms can exert outsized influence on ecosystem recovery, making them a focal point in future restoration strategies for other disturbed environments around the globe. Enhanced monitoring and research initiatives. The U.S. Geological Survey has intensified its focus on Mount St. Helens, making the volcano one of the most closely watched in North America. Thanks to expanded federal and state funding, the range of tools and technologies now deployed at the site is more sophisticated than ever before. Scientists are using a combination of ground-based sensors, airborne instruments, and spaceborne satellites to continuously monitor the volcano's behavior in real time. One of the most impactful additions has been the integration of continuous GPS and INSAR, interferometric synthetic aperture radar, measurements, which allow researchers to detect tiny changes in ground elevation, sometimes as small as a few millimeters. These measurements can be used to pinpoint the intrusion of magma or shifts in the internal structure of the volcano. New seismometer arrays have also been deployed to better triangulate the depth and intensity of earthquake swarms, offering more refined models of magma pathways and chamber locations. In addition, gas monitoring stations positioned near the summit and around key fumaroles are now capable of transmitting data in real time. These stations track emissions of sulfur dioxide, carbon dioxide, and hydrogen sulfide, gases that often escape as magma rises closer to the surface. Anomalous spikes in gas output can trigger automated alerts, prompting closer inspection or even field deployment by geologists. Perhaps most notably, the USGS has begun utilizing artificial intelligence and machine learning to detect subtle shifts in the mountain's patterns of behavior. Algorithms analyze years of archived data alongside current readings to identify anomalous trends, some of which might be imperceptible to human analysts. This AI-assisted approach is already proving useful in issuing early warnings and minimizing false alarms. Outreach and public preparedness efforts have also expanded. New mobile apps and interactive web dashboards allow residents and officials in the region to view live monitoring data and receive alerts tailored to their location. Educational campaigns have been launched to inform the public about what to expect in the event of renewed volcanic activity, making Mount St. Helens Helens, not only a geological hotspot, but also a case study in proactive disaster readiness. Together, these advancements mean that scientists are now better equipped than ever before to forecast potential eruptions and communicate risk in clear, timely ways. While Mount St. Helens remains a volatile force of nature, the tools to understand and prepare for its next move are finally catching up to its power. Life after ash. The eruption's devastation was immense, but it wasn't permanent. In fact, the regrowth has amazed scientists and defied many initial expectations. Hardy plants like fireweed and lupine were among the first to reappear, taking root in the nutrient-poor ash and spreading across the landscape. These plants, known for their resilience, enrich the soil through nitrogen fixation, creating favorable conditions for a broader array of species to follow. Alongside the early flora, microbial life began re-establishing itself in the volcanic soils. Scientists have since found thriving communities of bacteria and fungi in even the harshest parts of the blast zone. These microorganisms play a crucial role in decomposing organic material, enriching the soil, and forming symbiotic relationships with emerging plant life. Their presence laid the biochemical groundwork for larger organisms to return. As the landscape transformed from gray to green, animals followed. Gophers burrowed through the layers of debris, aerating the soil and transporting seeds and spores to new areas. Their tunnels helped create varied microhabitats, which attracted insects, spiders, and other invertebrates. Over time, these small creatures became food sources for larger predators and herbivores. Birds, once absent from the silent skies above Mount St. Helens, began to return as trees and shrubs provided nesting sites and shelter. Species such as the American kestrel and the mountain bluebird established new populations within just a few years. Amphibians, like the Pacific tree frog, found refuge in ponds formed by debris dams, while deer, elk, and even black bears slowly made their way back into the evolving ecosystem. This remarkable transformation turned Mount St. Helens into an outdoor laboratory for ecological research. Biologists have spent decades studying how life reclaims a barren land, using the site to test theories of succession, competition, resilience, and adaptation. The area has become a benchmark for understanding how ecosystems recover not just from volcanic eruptions, but from wildfires, floods, and human disturbance. In that recovery lies a powerful and hopeful message. Even from destruction, life finds a way to adapt, rebuild, and thrive. The rebirth of Mount St. Helens serves as both a scientific marvel and a symbol of nature's enduring strength, reminding us that resilience is embedded in the very fabric of life on Earth. If Mount St. Helens were to erupt again, the impact would depend on the eruption style. A slow, lava dome building event might stay confined to the crater, but a violent, explosive eruption like that of 1980 could once again devastate the surrounding forests, rivers, and communities. Lahars, volcanic mudflows, could race down valleys, destroying bridges and infrastructure. Ash clouds could halt air traffic across entire states. But this time, we're better prepared. Warning systems are in place. Evacuation plans exist. And thanks to the data gathered over decades, scientists have a far clearer picture of the mountain's moods. Mount St. Helens is more than just a volcano. It's a story about transformation. It reminds us that nature operates on cycles: eruption, silence, recovery, and that these cycles carry lessons not just for scientists, but for all of us. Life may be fragile, but it is also persistent. The mountain teaches us that from even the darkest moments, rebirth is possible. What comes next? Could Mount St. Helens erupt again within our lifetime? Quite possibly. But the real question is whether we're ready to listen. The signs are there, beneath our feet, in the air, and across the landscape. All we need to do is pay attention, because the mountain never truly sleeps. It waits. If you found this story as fascinating as we did, hit the like button and leave us a comment. What surprised you most about Mount St. Helens? Would you ever visit an active volcano? And don't forget to subscribe for more dramatic, science-packed explorations of our planet's most powerful forces.